Yes, good morning, everyone. We welcome you all for the forenoon session of our 5-day MDP program. So today we have a speaker with us, Dr. Mohammad Abdul Shukur. He received his PhD in 2023 from Electrical Engineering, IIT Palakkad, Kerala. He has done his MTech degree in Radar and Microwave Engineering from Andhra University and a bachelor's degree in Electronics and Communication from Acharya Nagarjuna University in the year 2016 and 2013. He is currently working as a postdoctoral fellow in Department of ECE, IIT Roorkee, Professor Karun Rawat. His current research interests include metamaterial-based absorbers, FSS, polarization converters, and now he has extended his journey towards active antennas, active reconfigurable intelligent surfaces, and RF power amplifiers. He has published more than 50 research articles in various reputed journals, and he is having 5 Indian patent and 1 US patent in his credit. So in addition, he was the recipient of Best Paper Awards in IEEE conferences like International IoT, Electronics and Mechatronics Conferences, Vancouver, BC, Canada in the year 2020 and the WAMS Conference 2022. So we welcome you, Dr. Mohammad Abdul Shukur, for our FDP. So, and the session is over to you.
Thank you, Dr. Rajesh, for such a wonderful introduction of mine. And I would like to thank you and VIT University for giving the opportunity to showcase my research work in front of multiple audience. And I'm sharing my screen now. Is my voice clear, Dr. Rajesh?
Yes, very much clear.
Can you see my screen?
No, we are not able to see the screen.
Can you see my screen now?
Yeah, now it is visible. Yes.
Okay. Good morning to one and all. Myself, Dr. Abdul. Now I am the postdoctoral fellow. Okay. Now I am going to tell you the few key highlights of the research direction in the metamaterial absorbers. The title of my talk is the recent trends in the design and implementation of multiband, broadband, and reconfigurable microwave metamaterial absorbers. The outline of my talk is as follows. First, I will give brief introduction about what do you mean by metamaterials, how the name comes, and what's the history behind that. Later, I will tell you what's the application of the electromagnetic wave absorption and why do we need and what are different application. And if you take the outline of the electromagnetic absorbers based on the performance, we can categorize these absorbers into three major categories like a multiband, broadband, and reconfigurable absorber. Then I will give the conclusion of my talk and few future scope for the young researchers who wants to pursue their research career in this domain. Let's come, what do you mean by metamaterials? Metamaterials are the artificial periodic construct of subwavelengths in size, which is a lambda g by 4, less than lambda g by 4, where lambda g is the guided wavelength of that particular frequency of operation. But these metamaterials exhibit a unique electrodynamic properties which are not readily available in the nature. First, for what do you mean by meta? Meta is derived from the Greek terminology which is called beyond, the properties which are not readily available in the nature. We will do some additional manufacturing or additional some fabrication process such that you will get those things. And why I'm focusing on this lambda g by 4? This lambda g by 4 because if the size of the unit cell is less than or equal to lambda g by 4, then the whole periodic surface will be effectively homogeneous, which means the refractive phenomena dominates over the scattering and diffraction. If you take any material, we can characterize characterize in terms of epsilon and mu. If you epsilon and mu, where epsilon is the electric permittivity and mu is the magnetic permeability. Where epsilon, we can if you have 4 categories where all the combinations are positive and all the combinations are negative. Either one is positive, other one is negative. If this epsilon and mu positive in for example, the main case is the isotropic dielectric medium. For example, if you take the metals at optical frequency, you can get the epsilon negative property. If you take the ferromagnetic material, we will get the mu negative property, but the combination of both epsilon and mu negative is not readily available. But from the mathematical calculation of Victor Villelago, he proved that if we could achieve these properties, there are multiple phenomena which can be possible. For example, here, if you take the electromagnetic wave propagation, which follow the right-handed propagation. Right-handed means your electric field and magnetic field and wave propagation detector follow your right hand orientation. For example, due to the epsilon and mu negative property, it will get the left-handed propagation. If you get the left-handed propagation, there are multiple phenomena which are not readily available in the physics. That means a negative refraction, the reversal of Doppler effect, reversal value of Cherenkov radiation, reversal of Snell's law, interchange of convergent divergence effect and convex and concave lens. But the thing here is, in many talks, people will tell this epsilon negative, mu negative, but no one will tell what do you mean by epsilon negative, mu negative. I want to emphasize here. For example, I will tell in the next slide. It's okay. And why the Metamaterial name came into existence. In 1996, Pendry group proposed a periodic array of copper wire with having a specific thickness and arranging a periodic manner of particular height. Then this property, you will get the electromagnetic response, which is having the negative epsilon. Same group, after a few years, they have proposed a periodic array of split ring resonators. We call it a split ring resonators. You will get the negative mu property. If you combine both, you will get the negative epsilon and negative mu. It was proved by Smith group. The thing here is why here the properties, whatever the electromagnetic response you are achieving, this is not because since it is a copper or since it is a dielectric, because of this periodic fashion and the arrangement of the cell. That's the reason you are getting this property. And one more thing, what do you mean by negative epsilon? For example, how this structure works. For example, when the electric field impinges on the surface along the rod, means along the tangent, it will induce the surface current. There is one relation, the constitute relation, D equal to epsilon E, where E is the electric field, impinges electric field, and D is the electric field density, electric displacement density, which is induced, which is caused to get the surface current inside this one. For example, if the frequency is very low, whatever the phase following by the incident electric field and phase followed generating by the currents are in phase. If you keep on increasing the incident energy, after some time at particular frequency, especially called plasma resonance, that particular frequency, this will come out of phase. That means the incident electric field on the top along this positive Z, and the electric field electric displacement vector will be on the bottom, D vector. That's the reason when in vector algebra, for example, if two vectors in opposite direction, you will correlate by the negative sign. That's the reason the negative epsilon and negative mu. Same way it will happen in the negative permeability, where B equal to mu into H. From that relation, you will get when H and B vector will get out of phase at plasma frequencies. If you can arrange these two at a time such that you will get both epsilon and mu negative. And one more thing, common misconfusion is having with a lot of researcher. Yeah, when we start with the metamaterials, people have told that means whatever the properties which exhibit epsilon and mu negative, we call it as metamaterial. Later the definition has changed, because it is not required such that if epsilon and mu negative should be there. Hello.
Yes, sir. Yes, sir. Please move on.
Yes. It is not at all required that epsilon and mu should be negative at a time. If epsilon and mu negative, it's a class of metamaterials. It's a class of metamaterial which is having a negative refraction, or NRA, negative refractive index. Okay, next come to our topic, which is electromagnetic absorber. Electromagnetic absorbers are specially designed materials which inhibits the reflection as well as transmission. There are different applications which has reported in literature. Here I am showing very few. For example, RCS reduction stealth technology, EMI suppression. RCS reduction stealth technology means this fighter jets has to be covered with the paints, which is a sort of electromagnetic absorber. When the radar send the electromagnetic signal, this due to the scattered energy from the aircraft will get back as echo. From the echo, that radar can track the signature of the aircrafts. But the thing is, when we go for the defense, this should be in stealth mode. That's the reason that RCS should be as low as possible, such that for the radar it should be appear as a bird. Some bird is moving like that. For example, electromagnetic suppression. Electromagnetic suppression means when you go for the complex board, one electromagnetic noise of the one electromagnetic component will disturb the performance of the other component. But we don't want that thing. In those things also, if we suppress the noise, is electromagnetic noise creating by the one component, that can then the performance of the whole circuit may improve. This is called electromagnetic suppression, where we use. And one more thing, this is a pyramidal foam absorbers. This pyramidal foam absorber, which we use in anechoic chamber for the R&D purpose, for measuring antenna, so many devices to characterize any EM-based instruments. And this is a mutual coupling reduction when we install many components which is sharing the common ground. Due to the common ground sharing, the surface currents will interlink. Due to that thing, these two components, where, for example, the radiating component will talk with each other. But we don't want. If we talk with each other, then what will happen? The crosstalk may appear. Do you want to reduce that mutual coupling? In those things also, we use the electromagnetic absorber. And before going to the metamaterial absorber, first I want to tell you what is the principle behind how the conventional microwave absorber works. I want to tell you the first conventional microwave absorber was designed by the Salisbury. Is a scientist named at that time, at the time of the World War I. Okay, Salisbury screen. What will happen? This design consists of a dielectric substrate is covered with the full ground. That means conductive backplane. If there is any metallic fully black plane, there won't be any transmission on the other side. The only will be the possible will be the reflection. Since the reflection coefficient of the metallic conductor is unity. And this is a resistive sheet which is having the free space resistivity of free space impedance, and which they provided for the impedance matching purpose. Once the incoming wave hits the Salisbury screen, what is the possibilities? Some part will get transmitted, some part will get reflected. The thing here is whatever the transmitted wave will hit back to the conductive plane, that will come in a 180 degree out of phase, and 1 degree out of phase due to this one, and it will achieve due to the lambda g4, it will achieve one more 90 degree, and due to the high density to lower density, it will achieve one more thing, such that the incoming wave and reflected wave will get cancelled each other. This is a sort of destructive interference phenomena. Due to that thing, what will happen? The total energy will reflected back is zero. Please note one point. If some energy implemented on any surfaces, there are 5 physics principles which will happen. One is the absorption, one is the reflection, one is the transmission, one is the scattering, one is the diffraction. If you take care of the size of the object, the scattering and diffraction phenomena we can neglect. Then the left principle is the reflection and transmission. For example, if you here blocking the transmission, that means transmission is zero. That means from the law of conservation of energy, the whole, if you can make the zero reflection, that means you can say that the whole energy is getting trapped inside the Salisbury screen. That will convert as a heat because of the resistive property. And what is the limitation of this thing? Because, okay, our job is done. The problem here is it is a narrow band, since the substrate thickness is dependent on the wavelength. And one more thing, the bulky in volume, when you go for the lower frequencies, the lambda g4 value will be more. You can't afford that much more thickness, and a large electrical thickness. And later the problem will be solved by with the help of Jaumann screening. In the Jaumann screen, we put multiple screens of different lambda g4 thicknesses. But the problem here is the problem of narrowband has been solved, because we are arranging the different resonance which will which will absorb at different frequencies, such that you will get uniform broadband response. But again still the problem is the broadband response, the cost of increasing effective thickness. We are increasing effective thickness since we are arranging the multiple layers, and which is a bulky in volume. Then, and what are the other different what are the other absorber configuration available in the literature, which is a Dallenbach layer. In Dallenbach layer, we use some conductive ink, we use some conductive coating. This conductive coating will absorb the EM radiation, and carbon nanotubes and a ferrite coating are magnetic balls, and so on. These things we use at the what I meant say at the pent level. And what are the limitations of this one, which is heavier in weight, obviously, and bulky in volume, is a cost expensive. The solution for all these things is metamaterial based absorber. Since it is a 2D structure, almost you can say quasi 2D, and you can be sure due to the low cost of PCB printing, it's easy to achieve. Okay, there are different configurations of metamaterial absorber. Here, my main focus is on the performance base, because In performance space, what are the two different parameters? In one has to see in the electromagnetic absorbers or metamaterial absorbers, one has to see the what is the frequency of operation, what is the absorption capability. According to frequency of operation, we can characterize the whole metamaterial absorbers as three different categories. One is the narrow band, that means which will operate at single resonant frequency or more than one resonant frequency, or you can say narrow band, in other case multiband. And one is the broadband, which will operate a huge range of frequencies, continuous range. And one is the reconfigurable absorber, where you can change switch the performance of the absorbers. Okay, first, why do we need the multiband absorbers? Multiband absorbers, conventional absorber working and limitations can be overcome, and the absorber utility in various applications and metamaterial absorbers have been explored here. The first perfect metamaterial absorbers has proposed by Landy. Landy, here what he has done, he has taken I-shaped electric field. It is I-shaped resonator, which is driven by the electric field. When the incident electric with a transmission line at the backside, when it is impinged with the electric field, what will happen? The surface current will develop. This surface current will start due to the slot in this one. It will act as some parallel LC circuit. Due to this one, this resonance, what will happen? It will give the perfect impedance matching with the free space. If from this relation, if you see, if you could achieve a perfect impedance matching, the reflection coefficient is low. There will be very slight transmission because it is not fully open and not fully closed. Partial transmission will be there, but he has designed at around 11.5 and 11.6 gigahertz frequency. At that time it was it is achieving a unity absorption, but the problem here is greater number of bands with better angular stability is required. Due to this this structure is a this periodicity of the structure is very huge, and getting greater number of bands inside a single structure is difficult, and controllability over the frequency response is needed. And what are the different narrowband absorbers which are already proposed in literature? There are different topologies which are proposed in literature, which is designed by different people, which is a 3 bands, 4 bands, 5 bands, and 6 bands. And for example, if you see clearly, the number of bands is created from the number of resonators. For example, if you count, due to this structure, you will get 1 band. Due to this gap, you will get 1 band. Due to the coupling between the outer resonator and this one, you will get 1 band. That means from the structure itself, you can tell what the structure it would help, what the structure it would behave. And one more problem here is due to the mutual coupling, because here you are generating the resonance because of the mutual coupling. This mutual coupling we can't control. That's the main problem in the literature. You'll get greater number of bands by placing a number of resonators. That is straightforward thing. But the resonance which is creating from the mutual coupling, that we can't control. One more problem here is we can optimize the frequency, then we can't control the absorption. If we want to optimize absorption, then we can't control the frequency. That means we can't control both absorption, that means unity absorption, as well as frequency at a time. Yeah, in literature they have proposed up to 6 bands, 7 bands like that. But next, and one of our design structure, which is a flower shaped patch. In this thing, we have designed a central flower shaped patch. This structure will resonate at 2 frequencies. The outer structure resonates at 1 frequency. For example, the outer structure will resonate at 5 gigahertz and 10 gigahertz and 14 gigahertz. These frequencies we have taken for the real time. How this structure work? When the electric field excite in X or Y direction, it will create a parallel resonance. Here parallel resonance we can clearly see the real part of the impedance is matching the 377 ohms, because we need the minimum reflection, and the imagined part is almost going to 0. And how can I say it is a parallel resonance? Because it is the imagined part is going from inductive to capacitive at the resonance frequency. If there is impedance match, there will be 0 reflection, which is almost minus 25 dB. If there is 0 reflection, since the structure is covered the other side with the ground, you will get near unity absorption at this frequency like 5, 10, and 14 gigahertz. And why we have designed for these 3 band? Actually, we want to explore this thing for the 3 different application according to the frequency. That means single design have to be explored for different applications, such as 5 gigahertz is a sub-6 gigahertz frequency for energy harvesting application, and 10 gigahertz for the RCS reduction application, and 14 gigahertz for the sensor applications. Yeah. First, here I'm showing how the sensor application one can demonstrate. Here the thing is, if you take the top FSS and you will keep some sensor layer, if you can vary the height of the substrate due to the effective change in the permittivity, the resonance frequency will vary. And one more, this we have demonstrated at the density sensor application. And if you simply change the airspace, then also the effective permittivity vary. Due to this thing, here we can say it is as a pressure sensor application. Due to the pressure, the gap between the two dielectric substrate will increase or decrease. Due to this thing, you can sense how much pressure we have applied on the top of this thing. And one more thing, this is for energy harvesting application. For energy harvesting application, what we do here, we cut this ring and we'll keep 2 resistors. Why? Because whatever the energy absorbed, we have to take out such that it can feed the RF energy harvesting circuit, which is a simple Schottky diode which will convert from RF to DC. There will be some filter steps will be there. There you will harvest the energy, and at that time it was getting nearly 60% at this particular resistor. There we demonstrate the same design for the RCS reduction application. For that we have fabricated a microstrip patch antenna that works at 10 gigahertz. There we have shown the RCS reduction process. And what are the problem definition for the narrowband absorbers? The problem definition for narrowband absorber, people have proposed from dual band, triple band, many. But the problem, as I told to you, the controllability over the absorbability as well as the resonant frequency is very difficult due to the mutual coupling involved between different resonators. Because if you can optimize one, to overcome this, we have proposed one decaband absorber which is based on concentric circular ring to achieve this operation. Yeah, we will see how this design work. Here, this is a simple conventional ring resonator. Here, what we have done, first we have designed this structure for different frequencies. First, we have taken the odd frequency, for example, 9 gigahertz, 11 gigahertz, 13 gigahertz, like that. Later, these are the design parameters. Thus, since it is a conventional circular ring resonator, if you see, the total lambda g will be the circumference of this circuit. From that thing, we have calculated and we have optimized this structure for the odd frequencies. The outer structure will resonate at the corner frequencies. If you see, the absorption will be 99, 98, 99, like that, almost near unity absorption. Later, we have optimized the same structure for the even frequencies. That means 10 gigahertz, 12 gigahertz, 14 gigahertz, 16 gigahertz, like that. These are the design parameters. Then what we did, there we have arranged in the form of matrix, like 1, 2, like that. You can see, this is for the odd frequencies, this is for the even frequencies. When we arrange it in a sort of matrix, the result of the response will work for undecaband. If we can take from 9 to some 20 gigahertz. 9 to 20 gigahertz. What's the novelty of this structure? Here, the thing is we are proving the controllability such that we are generating the intentionally 9, 10, 11, 12, like that. That means we are showing we can control the frequency, and as well as we are showing we are achieving near unity absorption. And one more thing I want to tell you, here one frequency is missing, I think 17 gigahertz. The 17 gigahertz we have not considered, because the thing here is we can do at the simulation level. When you go for the PCB fabrication, that tolerance we can't get with that dimension. That's the reason we omitted that thing, and we have achieved the utmost controllability as well as over the resonating frequency as well as absorbability. This is the equivalent circuit model which will tell you what is the physical phenomena behind the working of this structure. All the rings have design-based structure with a series capacitor and parallel LC circuit with series resistor, and the outer slotted patch is replaced with the inductor with same parallel LC circuit. And one more thing, when we have designed the any PCB based meta surfaces, if you see in the literature, people used to see this is the response for normal incidence, this is the response for the oblique incidence. Many researchers have the confusion with this. I just want to clear here. When when there is a what do you mean normal incidence? This is our PCB meta surface. This is at the center. When it is a normal incidence, the transmitting antenna will be aligned in this direction, such that the incident electric field along the is in the tangential, and magnetic field also in tangential. And the wave vector will be normal to that one. When once it hits to the metasurface, the same will happen for the reflected field. Since there is no zero angle with respect to the incident wave vector, there will be no change in the degree in the reflected fields. But what will this how the reflected field will travel? And reflection would be other than the design frequencies due to the PCB fabrication. This is a problem in narrowband absorber. A band of frequency will be absorbed for the case. This we call it as broadband absorber. And let's come for the oblique incidence. In oblique incidence, we have three cases, because when you go for the real-time scenario, we don't know from which direction the EM wave will come in incident on the meta surface. For that performance means one has to evaluate the performance of the design meta surface for different angle of incidence. For example, for the different angle of incidence, we can because it is a complete sphere, we call it as Pernicer sphere. For that, we can what I mean say differ in two cases. One is the transverse magnetic cases, one is transverse electric cases. In transverse magnetic cases, in transverse, the magnetic field vector will be tangential to the meta surface, and transverse electric field vector will be tangential meta surface. If you observe, the incident wave vector is making the angle. Due to the transverse magnetic cases, the electric field vector will make the angle, and due to the transverse electric cases, the magnetic field vector will make the angle. You can see the reflected field. The reflected field components will be like this. Here, one thing I want to tell you, because in the transverse electric cases, the electric field vector is always tangential. That means there is no variation in the field excitation with respect to electric field in terms of transverse electric cases. For example, in transverse magnetic cases, the electric field vector is along the is making some angle. That means some part of the electric field vector, that means some E cos theta, will link with the our design meta surface. That means with respect to that angle, that E cos theta will vary. That means some inductance capacitance variation will be there. And one more, I just want to tell you, these most of the structure which we design the PCB base, which is the electric field excited structures, which are not a magnet, because we are not using any magnetic material such that it will be excited with the magnetic field. That means since we are designing the electric field structure, our angular stability will be more good. It will be good for the T case more than the TM case. Yeah, this is the angular stability for normal incidence. That means we have changed the polarization angle at the azimuthal case. And when we change the angle in terms of elevation, we will get almost 45-degree stability for the T case and 60-degree stability for the TM case. Yes, yeah, this is a fabricated prototype, and this is a comparison of simulated measured data and good matching with the circuit model. Yeah, this work has been published in IEEE transaction, electronic compatibility, and so on and so. Yeah. Is there any possibility to achieve the other performance rather than absorption in a single device? Yes. Later we have extended the structure. We have taken the complementary of the structure. We have taken the complementary of the structure and we placed it on the back side. There we have shown the absorption as well as filtering operation. And the working model of the both structures are same, whatever I have shown you earlier. But the problem here, we have replaced the ground. That means here, if you see, when it is resonating, the other part is acting as ground. When it is eliminated from the other side, this part is acting as ground. That's the reason. If you see the impedance profile, that would be very clear. And one more thing, that means what is happening, we can select what are the frequency to absorb. That means we are achieving both absorption as well as filtering operation at a time. This is the reflection transmission response. The transmission is very poor, such that that's the reason you are getting a good absorption. This is the equivalent circuit model of this structure. And let's go to the other phase of this talk, which is a broadband absorber. Then why do we need a broadband absorber? Because when we design the multiband absorber, due to the many conditions like PCB fabrication error and whatever the design error and a solver issue, there is a slight change in the frequencies. because the thing, if you design at 3.5 gigahertz, it may work at 3.45, it may work at 3.55. It may not serve your purpose. This is one of the reason why we go for the broadband, because if you go for the broadband, it will cover this frequency. And one more thing, multiple applications, because same design will work for the multiple application. For example, here I have mentioned few applications with RF jammer in 5G and 6G communication, and energy harvesting and RCS reduction application. These are the multiple design, means which we have, which people have designed for the to achieve the broadband. This is asymmetric due to asymmetric structure. Due to the asymmetric structure, you will get the good absorption in one polarization. Due to this asymmetry in the structure, you will not get the good absorption in the other polarization direction. With the cross pole component will not absorb. You can say, instead of saying absorber, you can say it as a good linear to cross polarizer. It is a planar arrangement or consecutive arrangement of multiple cells. You will also get the means arranging multiple cells nearby, near multiple resonant frequency nearby. And one is the conducting base, and one is the welding lumped components. Yeah, we have means advantage as a pros and cons for every technology. The advantage is the bandwidth is enhanced, low profile and lightweight, and low cost and inexpensive. But the limitation is still broad bandwidth responses are in demand, and better angular stability and more compactness for sub-miniature applications. And what is the problem definition in broadband observer? Problem definition: broader bandwidth with extensive adaptability, compact profile, and greater angular stability is needed for microwave observer practical use. And one more problem, if you will come when you go for the broadband observer: grating loops. Grating loops are also a limiting factor for the absorption band, because the thing is, when you increase the you can say these are also called the higher order diffraction modes if you ask the physics people. And this grating load will come into the picture when you keep on increase the angle of incidence. And however, optimizing the cell periodicity rightly would minimize the effect of grating lobe. This is one of our design structure which we work for the X2 Ka band, almost 20 gigahertz observer. This structure is a multi-layer structure which is having, we have used two substrates separated by air spacer. The top layer we have taken a square ring with a split squaring, you can say. Here we have taken some 100 ohm resistor, 100 ohm resistors spacing differently. One can ask, means we can place 200 ohm resistor directly because since the resistance, but the thing here is when we split this resistor, the resistivity over the unit cell will be uniform. And this is the equivalent circuit of this one. This is a 3D model. I will show you the response. How this structure works. When we see the thing here is the real part of the input impedance almost equal to 250 ohms, which is near to 377 we can say, and imagined part will be close to 0 ohms. That means from these equations, there is only real part. If it is matches with the free space impedance, the reflection will be 0. Since the structure is covered with the metallic interface on the other side, if there is a minimum reflection, there will be only possible. This is the case which we can say. If the reflection is minimum, there will be the almost more than 90% of energy will be get absorbed over the broadband from 8 to 28 gigahertz. Almost it will cover 20 gigahertz bandwidth. When we change the angle of incidence due to the structure symmetry, when even though if you verify, means in the azimuth direction, the response is almost constant. These are called the grating loops. These are the grating loops. And one more thing, if you see, this structure is minimized such that sub-miniature, you can say that these grating lobes is falling outside the operation band. We are claiming it till 28 gigahertz. These grating lobes are outside the operating band. We can say the structure is stable up to 45 degree. And this is the reason what I said to you. If you take a simple 220 ohm resistor equivalent, this absorption is not uniform. And if you take the two 110 ohm resistor, if you split, the absorption is uniform. That means you will get uniform absorption due to the uniform resistivity over the periodic unit cell. And this diagram will tell you, because here the thing is how the energy is getting absorbed. Because the thing is, and what are the lossy components? This structure work on the resonance. This metamaterial based structure work on the resonance. If it is resonating, the real part of the input impedance purely resistive. Due to the resistive nature, the energy is getting absorbed. But the problem here is this structure won't help if you take the simple metamaterial resonator, which will not help for the broadband. This thing will be overcome by placing a resistor. If you see the literature, there are two types of broadband absorber. One is the circuit analog absorbers. One is the capacitive circuit absorbers. The circuit analog absorbers use the band stop circuit. Band stop because this is a parallel LC circuit, series LC circuit. The other case use the capacitive circuit method where we use the low pass filter. And one more thing, if you see, we have varied for different cases. From this thing, if the resistor is 220 and this is the almost the absorption. If, for example, if you place the resistor 0, if you place the resistor 0, that means we are mimicking the perfect metamaterial absorber without any resistor. That means your absorption has been fallen. That means almost zero absorption. You are getting a resonance at this frequency nearly 7 gigahertz, at this frequency nearly 30 gigahertz. But the thing is, there is no impedance matching in between the frequency. That's the reason the whole energy is getting reflected back. The absorption is 0. That means when you place the this lump resistors, what will happen? It will achieve the broadband impedance in between the frequency, such that these two frequency will boost up, such that in between the band, can achieve the broadband absorption. And one more thing I just want to tell you means what are the different resonances exist. For that reason, one has to study the surface current distribution for those patterns. We have taken the two frequencies, 10.4 and 25.2 gigahertz. If you see, the thing here is at this 10.4 gigahertz, that the surface currents on the top and the bottom ground anti-parallel at same nature is exhibiting at the 25.2 gigahertz. These two are the resonance which control the you can say the cutoff frequencies of the absorbers. And if you can operate in between the cutoff frequency, you will get the uniform absorption. And one more thing, due to this currents are anti-parallel, we call this resonance as dielectric resonance as well as a magnetic resonance, since it is resonating a magnetic dipole, the current circulating loop. Yeah, this is our fabricated prototype, and this is the measure result, which shows a good matching up to 45 degrees. Yes, later we have demonstrated this work. Where the same antenna which we use, the 10 gigahertz antenna, we placed and we have observed the RCS reduction pattern, which shows up to 13 dBsm RCS reduction for different angles. And since it is a broadband absorber, although we vary the frequency of the, it can cover the almost a broadband response. And whatever the energy absorbed by the absorber is dissipating as heat. How can we say that thing? For that thing, we have used the IR imaging concept to get the temperature profile measurement. This is a fluke IR camera which you place in a sample. When the transmitting candle is illuminating for at least more than 2 minutes, these unit cells will get heated up. If you see, this is the out of the band frequency, this is the in band frequency. That means this is around 15 gigahertz, this is at 4 gigahertz. If it is at 4 gigahertz, the energy absorbed will be very low. If you can see very clearly, this is 2 degree variation in the 2 degree rise in the temperature for 2 to 3 minutes of illumination, EM wave illumination. And this is the state-of-the-art table which compare how this design is novel compared to the other reported literature. And let's come to the last phase of my talk, which is a reconfigurable absorber. And why do we need the reconfigurable absorber? For example, once means whatever the narrow band, whatever the broadband absorber, which they designed are passive. Now, passive in the sense we have not used any active component like diode or transistor or anything. For example, but in real-time practical scenario, we want one application such that it can serve multiple purposes. That means we need a reconfigurability in terms of performance. One has to, but the thing here is, if a broadband absorber can serve the purpose of multiple frequencies, why do we need the reconfigurable absorbers? For the reconfigurable device, one will go when for example, I can say in terms of amplifier thing, everyone knows that the gain of the amplifier as well as bandwidth is constant. That means if you want a high gain, you have narrow bandwidth, but the performance will be more. If you want to compromise gain, the bandwidth will be more, but your performance will be low, since it is covering the whole band. That's the reason. But in many applications, we want to operate at multiple frequency as well as you want efficient operation. For that cases, broadband applications will not work. We need to go for the reconfigurable. And I will tell you what are the advantages over the passive structure and modeling of RF switches and different application single devices. Need of reconfigurable devices, as I already told you. Once a design is finalized, the device performance is unchanged. which is not recommended. The flexibility is performance achieved by altering the design state mechanically, but due to the cumbersome mechanical adjustment in a reconfigured device, switching device function in a quick reaction time is difficult if the design is mechanically adjustable. Then FSS based absorber passive structure with fixed reflectance. However, lumped resistor may expand the absorption bandwidth, as I told you, the broad, but achieving broadband absorption won't be sufficient since the response is unchanged. Then, to address this issue, such elements add a pin diode, vector diodes, and integrated metaparticles for tuning the device functionality electrically. Then, the solution for this is active frequency alternative surface may reconfigure the performance due to the availability. And this is how one can model the pin diode, which is in the forward bias and reverse bias. Pin diode will work as simple resistor in a forward bias. In the reverse bias, it will work as a simple capacitor. Pin diode of a particular device. And if you take the vector diode, you can the difference between the pin diode and vector diode. Pin diode only have two state. One is on state, another off state. That means within vector diode, you can adjust the voltage continuously, such that you can say it is a variable capacitor, varicap. This is the equation one can get the information, means which type of vector diode, which type of capacitor is needed, what is the value of capacitance needed, what is the voltage handling, and which diode, which series diode will give that capacitance. Yes, this is one of our reconfigurable multifunctional wideband FSS at sub 6 GHz. Here the design structure is, we have taken the butterfly type structure, which is loaded with the lumped resistor and at 4 cases. On the other separate, we have taken the inductive grid, where we have integrated the pin diodes, 4 integrated pin diodes. I will show the fabricated prototype at the last slide. Later, then we have separated with the ground. Here we have adjusted for different topologies, such that this same structure will work as a wideband absorber and band notch absorber, as well as full and half power reflection. If you vary the configuration, if you see the impedance profile at different cases, since if there is no resonance, it will act as a simple absorber. If there is a resonance, since it is a parallel AC, it will have a band stop filter. Due to that band stop filter, you will get notch in the performance, such that this response is the band notch response. And this one, if you adjust the height of this thing, it will act as a high power and full power reflection. Sometimes this device will not only absorb. If you want to reflect the full power, if you want to reflect the half power, it can do over the wide range of frequency from 2 to 6 GHz, sub 6 GHz. And as well as filter. If you remove the other side of the other side of this design is covered with the ground. If you remove this thing, if you remove this ground, this will act as some band pass and band stop filter based on the on and off state condition of the diode. And this is the equivalent circuit model of the circuit and of the metaserver. And this is a good matching is observed between both the EM solver model as well as circuit simulator model. And this is a fabricated prototype of different stages of the metaserver. This is a integrated pin diode. This is a biasing pads where we can bias, and this is a good matching is observed between the simulation and measure results over the frequencies. And this is a measurement setup. This is a DC supply which for biasing of this diode. And this is a performance comparison. What's the novelty of this design structure? And let's come to the conclusion. The conclusion of my talk is as follows. The controllability of both absorptivity as well as resonant frequency is demonstrated using a simple concentric circular ring FS base. This technique extended for designing the dual band functional absorber as well as reflector configuration that we have already done. And one more thing, one can extend this work such that to further design of wideband absorber. And broadband absorption has been explored with CA along with the reconfigurable absorber also. And what is the future scope from this work? As I said to you, I have designed the undecoupled band absorber. That means I am arranging the even and odd frequencies nearby. If one could generate a very close nearby frequencies, that would be the very novel work. That means we are replacing the lumped components. We are not we may not use any lumped component. Again, we are achieving the broadband absorption with simple PCB. That would be the novel work. This is this thing. And broadband energy harvester. And we have shown the energy harvesting part, but thing is, getting a broadband energy harvesting is very difficult, challenging part. Means there are many papers which are already reported in literature which shows the broadband absorbers, but no one has shown the broadband energy harvesting circuits. One can design the broadband energy absorber and direct the work towards the broadband energy harvester. And I want to tell means how we have designed this structure, how we have fabricated all these things. Yeah, if you go for the PCB fabrication techniques, there are mostly the two techniques. One is called chemical or wet etching technique, or a dry etching. And other techniques like screen printing, laser micromachining, inkjet printing are there for the other types of design. And there are one more case called additive manufacturing, 3D printing case is also there, where we can use the PLA or different types of material to print the microwave absorbers. And one more technology is there, which is called microfluidic technology, like liquid material, that means e-gain and liquid dielectric material, such that you can get the reconfigurable operation with the help of liquid flow inside the material. And one more case, you can say origami structures, which is foldable, which is mostly preferable for space application. And one more topology we call 4D shape or memory polymers, which we mostly use for the application, for the rugged application and military cases. If you take the chemical or wet etching, this is the process. I am showing this slide for the young researcher who is new to this field. If one want to do the design from their own hand, first we have to finalize the design in EM simulator, export the Garber data. Then we have to generate the first mask file in the photo plotter. Then we have to then we have to cut our PCB in the substrate cutter, then paste our PCB along with the mask sample PCB, input in the heating oven such that the impression will come, and put the vacuum spinner, and let's expose the UV light such that whatever the thumbprint on the mask will be on the PCB. Then apply the photoresist chemical. The photoresist chemical will be positive or negative. It depends on which type of UV light you are using, and what do you want, and which type of mask you are using. And you will keep it in the heating oven. Once it is done, you will place in the corrosive chemical light HCl and zinc chloride and ferric chloride solution, such that means wherever the UV light is not exposed, that chemical will left, and that part will left. Wherever the UV light exposed, that part will remove. It depends on the positive or negative masking thing. Then your prototype ready. This you had to do in continuous step. And when we go for these are the devices which we use at our IIT Palakkad lab. This is substrate cutter and heating oven. This is a vacuum spinner and UV exposure unit. And this is a rotatory flax where we will place a PCB. And this guy will rotate, and due to the corrosive chemical, our PCB will get ready. These are the key steps which I have already told to you. And one more challenging part is the mounting the lump resistor, diodes, everything. For mounting the SMD process, what we do in industry, we'll prepare the stencil file. File will prepare with the laser metal marker. This laser metal marker will give you the accurate slot, such that that will help to place the components. Later, the stencil file is a thin stainless steel sheet, SS sheet, which we place on our PCB device. This will be like this, and we will place in the stencil aligner. Once it is done, we will place the solder paste. You will drag, and once it is done, then we will place the SMD component and we'll put in the heating oven with the adjustable temperature profile. With this temperature profile, we will get from the data sheet of the soldering paste which we are going to use. And these are the key references of my talk. And thank you very much for your patience.
Thank you, sir. Thank you so much for your presentation. And now we can take queries from the audience. In case if any queries, we can take. Yes, if you have any queries, please get it clarified with respect to the absorbers or metamaterial or FSS related things. You can get it.
Sir, I have a question. Sir, in the last design where reconfigurable FSS has been designed, then
Yes.
how the diodes are being biased? I mean, how the biasing is provided? If possible, please explain, sir.
Okay, you are asking how we are biasing the diode, right?
Yes, sir. The
Yes, yes.
diodes are in
Yeah,
one
1 minute.
condition on and off.
Yes, yes, yeah. See, I can explain you from here better. Yes, if you see the close view from the center point, from the see, yes, this will be the see. First, concentrate on one unit cell. See, at this center point, I have taken one biasing line. If you access this center point, you are accessing all the positive nodes of the diode, right?
That means there is a feed connection, right?
Yes, 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 yes. That I will place. The DC feed will be there here. And if you, yes, at this point, if you access any of the point, you are accessing the negative point of the diode. That means cathode of the diode. That means if you see this fabricated circuit, if I can zoom, this is there is a center which is feeding, and this is at the edges you are accessing the points. And one more thing, when we are deciding the biasing voltage and current, that we have to check the data sheet. For example, first you have to check whether this configuration we have connected in series and parallel. If you have connected in series, the voltage will be voltage will be same, and current you have to adjust such that the whole diodes will feed up. If you operating in parallel, what we have to do, the voltage has to be add up and the current should be the same. Have you understood?
Actually, sir, it is very difficult in this view. If possible, sir, in the single unit cell where the
No. Yes, no issues. Yeah, yeah. This is already a published paper. There I have given very clearly. You please
okay,
go
sir.
through that paper. Yes, yes.
Okay,
If you
sir.
have any
I
query,
will.
you can contact me. No problem.
Okay, sir. Thank you, sir.
Yes, yes, yes.
And sir, one more question, sir.
Yes.
FSS and meta surface.
Mm-hmm.
Oh, I mean, which one will provide the better reflection, or is there is any difference?
Meta surface is a very big domain. FS is a class of the meta surface.
Okay. So FSS is a
FS,
class of meta cells.
yes, yes, yes. Actually, many people will confuse. Some people will say FSS based observer. Some people will say meta surface based observer. But actually,
Yes.
if you ask me what do you mean meta surface based observer, as I told you that lambda g by 4. If your size of this unit cell if less than lambda g by 4, then you can see it as meta surface based observer. Otherwise, you can say FSS based observer. That is the best statement I could say.
Sir,
If the
please
size,
repeat. If the size.
yes, yes. What I'm saying, the thing is only see if you take any metallic surface with some slots and cut, it will act as a resonator, right?
Hmm.
That resonator is nothing but a filter.
Yes, sir.
That filter we call it as frequency selective surface, which is called
Yes.
spatial filtering.
Hmm.
Right, but the
Yes,
thing
sir.
is if that spatial filter which is having the size which is less than lambda g by 4, you can say it is a meta surface based observer.
Okay, sir. Okay, sir. Thank you,
Yeah,
sir.
yes.
Any other questions?
Sir,
Any further?
sir,
Yes.
sir,
Yes, ma'am.
I'm doing research on FSS, sir. So
Okay.
especially I have a doubt about the polarizer converter in a patch-based FSS design. If the signal has already been stopped at a specific frequency, why would a polarizer converter be necessary, sir?
1 minute. Are you asking about this design?
Not a observer, sir, not a just polarizer design. If we design based on bandstop filter, that is a patch-based FSS design.
Okay.
If we stop the band signals at the specific frequency, then we convert the polarizer linear to circular. What is the necessity of that converter?
Here I'm not talking about the polarizer, right? I'm talking
Yeah,
about
sir.
the
Yeah, sir.
absorber.
Yeah, sir. Yeah,
Yes, yes.
but I referred your many papers based on polarizer. That's why I'm
Okay.
asking. Okay, sir.
Okay, can you please repeat the question?
Sir, if we design the FSS based on patch, that's why it's
Based
act as a
on
band
patch. Okay.
patch. So it acts as a band stop filter.
Yes.
If the signal has already been stopped, what is the necessity of polarizer converter?
No, polarizer converter having different application. What is the necessity? There is nothing related to the band stop and this one.
Yes. You you presented, you published some papers based on a polarizer converter based on a patch-based FSS design. Am I right, sir?
Okay, I'm not getting means. See, means I have published in many papers. I'm not exactly getting. Please take my mail ID. You can contact me there. I can explain
Okay.
you there.
Okay, sir. Okay, sir.
Okay,
Sure.
because yes.
Sure, sir. Thank you, sir.
Yes, no issues.
Any other questions?
Yes, sir. I have one question. So,
Yes, please.
what is the effectiveness of this equivalent circuit, sir? How it helps us in design, or it helps in validation only?
Sir, it will help in
Engineering also.
validation. Sir, it will help in validation. How can I can tell you this thing? For example, why do we need EM solvers? First, ANSYS or CST. Why do we need? That is the first question. The first question, because the thing is, for everyone knows that the antenna resonates at lambda by 2, lambda by 4. Everyone knows. Then why we are doing this? All these things set up in this thing. Because when you go for the circuit, it will not tell you the radiating properties of the structure. It will only deal with the voltage and current, KVL KCL, right? But if you want to deal with the radiation properties such as that absorption, reflection, whatever phenomena happening in the space, that you can't tell with that circuit. But the thing here is, means whatever the phenomena is happening in the space, this is because of the circuit. If there is no if there is some function happening in the circuit, that's the reason you are getting that phenomena whatever you are desired, right?
Okay.
Yeah, if you want to make sure, means whether a phenomena is going correctly or not, we have to compare with two different solver. One is the circuit simulation, and which we works on mostly on method of moments, and one is the EM solver which work on FDTD and FEM solvers, finite element method.
Okay. So helps in validation mainly.
Yes, it's help in validation and clear understanding, means whether you have understood this. This is for example, as I said to you, this resonator is giving one resonance, this resonator is giving one resonance, right? 1 minute, I can tell you in better way. Yes. Sir, see, here we have, for example, 5 resonators here and 5 resonators on the opposite, means cell 1 and cell 2. We have total 10 resonators. 10 resonators are giving 10 band, and the outer, there is one metallic slot patch which is called inductive grid. If you see, I have mentioned this is one resonator, right? This is one resonator. I mentioned with label I. That means there are 10 copies of such that I1 to 10. This will give 10 resonance frequencies, and one more slotted patch is giving the outermost resonance. That's the reason I kept. You are getting 11 resonance frequency. You are receiving 11 resonators, but the resonance are opposite type. One is the band pass type. One is a band stop type.
Okay.
I hope I made it you clear.
Yes.
The answers, let us conclude.
Yes, sir. We can conclude. If there is no query.
Okay. Thank you, sir. Thank you, Dr. Abdul, for your valuable time, and even after rescheduling, you have given a very good content.
One more time, I sincerely apologize for
No issues,
postponing
sir.
of this topic.
It so happens, no issue.
Yes.
So anyway, thank you.
Yes.
Thank you, sir. Thank you so much. Thank you, participants. So we'll meet in the afternoon session by 2:30. The speaker is Dr. Nasimuddin from Infocom Research, Singapore. Thank you.